Welcome back to our final lesson in electricity and magnetism. Now, we left off yesterday talking about how Faraday's law of induction saying that if you cut through magnetic field lines with a wire, that you can create a current and a voltage in that wire. Today, we're going to look at two practical applications of that. Okay, and I'm going to give you a nice little background because there's a beautiful movie that came out about this and a nice, great story about Edison, Tesla, Westinghouse. Some of you may already know what I'm talking about. If not, we will talk about it tomorrow in class. But we're going to look at the AC generator. Okay, the AC generator is a device that uses the principles of Faraday's law in order to generate an electric current. And so what happens is, if you take a look at this, we have this loop right here, and I'll highlight it in red. This is what's known as an armature. And that armature consists of a wire coil or many wire coils. And as it's spun, it's cutting through the magnetic field lines that are here. And so since it's a wire cutting through the magnetic field lines, it is creating a current that is being produced in that wire coil and then being sent off. But because it is spinning every half turn, it switches the direction. The other thing too we need to remember is that when it cuts through perpendicularly, that's when we get a maximum amount of current. When it moves parallel, we get zero current. And so that current is going to fluctuate back and forth, and it's going to will give us what's called alternating current. Now, we've talked about AC before, but AC, if you look at it, is represented by, it goes up and down, back and forth in one direction. So you get a maximum. That's when the wire coil is cutting perpendicular through, and then you get zero, the minimum, again, zero, we'll say, because at that point down, there's no current, just the other, this is just max in the other direction, so a negative max, okay? But here, when it gets minimum, that's when it's moving parallel. And the faster you spin it, the more of these cycles that you get. So you get a back and forth, back and forth. Number of cycles that it completes in one second is called the frequency, and it's measured in hertz. And we'll talk about that more when we get to waves as well. Okay, here in the United States, we use 60 hertz as the standard. Now, the magnitude of the EMF or the voltage and the current that's coming through depends on the rate at which we cut through those lines. So again, remember, from Faraday's law, the EMF induced is equal to the number of loops times the number of lines that are cut per second, delta T. Should be a delta phi and a delta T. Okay? And we said before it was also equal to VBL. Okay? In order to find out that EMF. Well, by changing that in our generator, what we can do is we can increase that by changing it in 4 ways. We can speed up the rotation. The faster you spin it, the faster it's going to cut through those magnetic field lines, the more current, the more voltage you get. The number of wire loops, obviously each wire loop will produce a certain amount. So if you increase the number of loops, you're going to increase the same amount. Yep. Strength of the magnetic field, more magnetic field lines to be cut, more current is being generated. And lastly, this is something new that we didn't talk about in our diagram. But remember when we played around with the electromagnets, we said that the core of the electromagnet concentrated those magnetic field lines. Well, if you concentrate them, you can fit more into a little space, and therefore more lines will be cut. And so this is something that we can change that armature's core's permeability, how much it compresses and combines those magnetic field lines. Okay? Now, the other device that we're going to look at that runs off of AC and this whole principle of inductance and everything else is called the transformer. And I'm going to draw a diagram. Now, you're going to get this diagram later on, too, a much happier, prettier one. Okay, but I want to start with this one only because it's a really good idea. And we're going to start with the primary side or the input side. And this we'll call the secondary or the output. And what this is, all this is an iron box. Okay, an iron square, if you will. And what we're going to do is we're going to wrap wire coils around one side of that square. I'm trying to make this look three-dimensional. It's as best as I can do. Okay? And so we're wrapping wire around it. And what we're going to do is we're going to apply an alternating current. Okay, so this current is going to go first in one direction, then the other. So it's going to be constantly changing. Now, think back to what Oersted proved. Oersted showed that if you have a current moving charges, you create a magnetic field. And so this alternating current in my primary will generate a magnetic field. And I hate to put on arrows on this because it's going to be constantly changing direction. It's going to go around. And I should never ever have them cross. Actually, let me erase that because I don't want to be that guy. Got it. Go around like this. Yeah, they're squeak through. Boom, boom, boom. You get the idea. So we have magnetic field lines being created. And because this current is going from 0 to something back to 0 again, think about the alternating part. Their magnetic field is going to go from 0 to something back to 0 again. And then because it alternates, it's going to go back in the other direction. So what you have is you're going to have a changing magnetic field inside that box. Okay, and I put the arrows as having going clockwise right now. They're going to switch back and forth, back and forth. You have that changing magnetic field. Well, on the other side, on the secondary or the output side, I'm going to do this in orange. I'm going to have another set of coils. And over here, I'm going to increase the number of coils we have. Again, I'm going to try to go three-dimensional best I can. And so these coils have that changing magnetic field they're being changed as through those coils. And so that changing magnetic field creates, so I'll put this in, I'll take it back in green, creates a changing current. And now you're thinking to yourself, okay, so great, I put in alternating and I got alternating. What's the big deal? If you look at the different number of wire loops, that ratio of the wire loops is the exact same as the ratio of the voltage that's created. And so if I have a 1-to-2 ratio from primary to secondary, my voltage will increase by double. Because by the changing of the magnetic field, by changing the number of loops, we change what is being created. Now, again, I put in current here. Remember, we're also talking about an EMF. We're applying an alternating current or an alternating EMF. Okay, same thing, creates a changing current or a changing EMF. Okay, so just know that we're dealing with it because you can't have a voltage on a current, vice versa. Okay, so what we're doing here is by changing those number of loops, we change the primary current, primary voltage coming in to something else. And so it's constantly changing, okay? So again, you can see how this is changing magnetic field. We'll contact the second coil, create induced EMF in it. It's called the current to flow as well. The strength of the induced current depends on the number of turns or coils, I should say turns or coils, in the first and second. Okay. Now, there are two types of transformers. There's a step-up transformer, and that's the one that I drew first. That one has more coils on the secondary than it does in the primary. And so in this is like something we use at power plants. Because what we want to do in power plants, the amount of energy that you lose in transmission is directly related to the current going through. So the higher the current, the more energy loss you get in going through the line. And so we want to keep our current low, but that means taking our energy high. And so these you will find at power plants, and these will push out our electricity to be high voltage. Okay? And so if you've ever seen like the high voltage lines, like if you're traveling along Route 60 to Dunkirk, okay, you see those high, big, tall towers, those are high voltage lines. Okay? The other place where this is used is actually in fluorescent lights. Okay, in fluorescent lights, if you look at those, they actually have transformers on them because those need a high amount of voltage because the charges on the inside need a lot of energy in order to make the jump. So just another example of, neon lights as well, also use step-up transformers. Step-down transformers flip the script. So we have more coils on our primary and less on our secondary. And for that, what ends up happening there is now your voltage is stepped down, okay? And there's reason for it that we'll discuss in class tomorrow. Why do we want to have a step up? Why do we want to have a step down? What's the advantages of it? Who cares? What's the point? Okay, but this would be like what's used on the outside of the lines. If you've ever looked at electrical lines and you've seen like those gray garbage can looking things, those are step down transformers to make the voltage less, so it's not as high when it goes from the electrical line into your house. You don't want high voltage in your house. We'll discuss why later on. So these will convert their energy back and forth, and this is the primary reason why we use alternating current in our households, in our everyday lives, rather than direct. We'll have that conversation. The last tidbit is just giving you the formulas, okay? And here's the beautiful thing about it. If I had you build one of these in class, if I had you build this, even if I had you build this ugly thing that I built right here, the efficiency of these is astronomical. Okay, you could build one in our classroom with the stuff that I have, and it's going to be between 90 and 95% efficient of the energy you put in compared to the energy you get out. And so because these transformers are really, really efficient, we can say that there's a law of conservation of energy there, LOCO-E, well, in terms of, law of conservation of power. Let me erase the O, the F. Okay, put in terms of power, there's a law of conservation of power there because the energy you put in is equal to the energy you get out. And so in that case, we can say that the power you put in is equal to the power you get out. And so remember power, so that would be like the current in and the voltage in would equal the current out and the voltage out. Okay, so you should see by this there's a trade-off. If I want to make my voltage high, I make my current low, and I'll rewrite that actually so that V in over V out is equal to I out over I in. There's an inverse relationship here. Okay? And it turns out that we said this before, but the ratio of the number of turns on the input to the number of turns on the output is exactly equal to that of the voltage. Now, you won't see it as in and out generally. I'll write this last thing and we'll call it a day. But normally you'll see NP over NS equals VP over VS equals IS over IP. Okay? So for primary and secondary rather than in and out. Okay? So we'll discuss this in more detail tomorrow in class. And this is the end of electricity and magnetism. So we'll spend a lot of time now preparing for our next big monster test on all electricity and magnetism. But you have the knowledge, we're gonna do great. So, hey, everybody have a great day. We'll see you later, bye.